All right, guys, for this fourth one, we have the famous tree diagram. And so they tell us that a large international sports team tests their athletes for banned substances. Okay? They interpret a positive test result as meaning that the athlete uses banned substances. So it's positive if they use. A negative test result means that they do not. The probability that an athlete uses banned substances is estimated to be 0.06. And so, especially for probability problems, you need to really check if everything that they give you is in your diagram or not. Okay? Do not take it for granted. Double check. Usually in geometry and trigonometry, whatever they say like here is going to be in the diagram. Okay? Usually. Almost always. In my experience, is practically almost like always. Okay? But for probability and stuff like that, they don't always put it. See? For example, this first one, the probability that an athlete uses banned substances is estimated to be 0.06. And so, uses bad substances, kapow, kapow, 0.06, there it is. See? And so this first one, it's what they tell me is already in the diagram. Okay, we're happy with that, ¿cierto? Cool. This next one we have if an athlete uses bad substances, so kapow, the probability that they will test positive is 0.71. So that is kapow, 0.71. There it is. It is also in my diagram. See? Notice how in this case we had like a two-stepper, ¿cierto? Como kapow, kapow. And this is because if an athlete uses banned substances, so I'm in this part of the world, the probability will test positive. I go this way. See? So whenever they put the if word, very important, um, sort of like a conditional probability, stuff like that, you are going a certain direction, you are limiting part of your options. See? Why does it limit part of my options? Because when they say if they use banned substances, you know you're in the banned substance world. You actually forget about everything else up top and you only look at the bottom. Okay, that is the power of the if. That is the power of the conditional probability. Anyways, whatever. This second thing, the 0.71, does show up in my diagram, so I am relaxed. Okay? And this last part, as we can see, has if an athlete does not use banned substances, so kapow, now I'm going this way, does not use, right? The probability that they will test negative is 0.98. And so this testing negative right here, the 0.98, I have to put it, and I got to put it right there. 0.98. See? Let me just, let me make that a little more pretty. So 0.98. All right, I don't know how much prettier that was or not, but whatever. Point is, this third thing, I now just put it into my diagram. There it is, there's 0.98. So now I'm ready to do part A, which says using the information given, copy, blah, 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 complete the tree diagram. See? Now, these are some really easy 2 points, and you just have to know the intuition of the tree diagram. So I'm going to take a little bit of time explaining it, and the rest is going to be a little faster. See? Anyways, in the world of probabilities, ladies and gentlemen, your probability basically has to add up to 1. Okay, and I know that right now sounds a little bit weird, but your probability has to add up to 1. All right, there's a couple of things going on here. See, on the one hand, when you consider all scenarios, the probability of everything added up together has to equal to 1. See? On the other hand, because it adds up to 1, this 1 tells me that it's, where is my equal sign? This 1 means 100%. Ah, so 0.5 means that it's 50%, and 0.05 is 0.0, sorry, it's 5%. If you memorize these three numbers, you're good to go to find anything. For example, I can tell you, well, what is this in percent? And you look at these other cases, you get the intuition, you know that you have to move the 0 a couple times. This is going to be 0.7%. Kapow. Just like that. And I can also give you 0.13%. And you'll tell me, see, that is 0.0013. whatever, man. You can go from decimals to percents. That's what I'm trying to say. And 1 is 100%, and your probability has to add up to 1. Why? Let's say you're leaving school, for the day. You got tired of the B. You just want to go home and play, I don't know, League of Legends and fall into depression or something because it's League of Legends. Um, and so if we talk about what you do when you go home, right? Uh, the things you can do once you leave school, right? You might tell me there's a 50% chance I go home. You might tell me there's a 32% chance I go, I don't know, for a walk. Maybe there's an 8% chance that you go get something to eat. See? And then there's a 10% of maybe just whatever, sleeping. Okay? Point is, you can put a lot of percents here. You can put all the different scenarios that you want. But these percents add up to how much, ladies and gentlemen? These percents, lo and behold, add up to, and this is the dramatic moment, all of these percents add up to 100. That is the point of probability. That is what I mean, that your probability has to add up to 1. If you consider all the different scenarios, your probability has to add up to 100%. Okay? The thing is, in a tree diagram, you don't have all these different options. I mean, if I were to try to express this in a tree diagram, it would literally look like this. Okay, that would be my first part of my tree. This might be my second. Okay, it's confusing, it's hard. See? And so the cool thing about the tree diagram is that it simplifies it a lot. It says, okay, so instead of taking all these crazy scenarios and different scenarios, you have to boil it down to 2. And so there's either, I don't know, a 50% chance that you go home or a 50% chance that you play League of Legends. Okay? And these numbers can be different. Maybe it's 35, and over here it would be, I don't know, 565, right? These numbers can change, but it's only 2 options. Okay, so the tree diagram boils it down to 2 options. Okay, that's the main idea. It boils it down to 2 options, and your probability has to add up to 1. Okay, why is this useful? Why is this guy on YouTube saying all this shit? He's saying all this shit because in a tree diagram, there's only 2 options, and because your probability adds up to 1, then that tells you the massive piece of information that this plus this is 100%. That this plus this is 100%. And that this plus this is 100%. Ah, okay. Okay, so for example, here, when they use bad substances and they test positive and you get 71%, well, this plus this is 100. And so 0. So my 100, right, my 1 minus 0.71 is the testing negative. Oh shit, so this is 0.29. Okay, okay, tell me more, tell me more. And so if you keep filling in the tree diagram like that, keeping in mind the 2 options, the thing that they add up to 100%, what do you discover? That over here, when they use banned substances and you get 6%, the probability that they don't use banned substances is 0.94. Because 1 minus 0.06 is 94. Guys, that is the key idea, okay? Tree diagrams, they add up to 100%, each of the 2 like sticks, see? Each of the 2 alternatives. And the reason this happens, which is actually in your formula booklet, is this thing called complementary events, okay? What this means is that you either go to them all or you don't, okay? You either flip a coin and get heads or you get tails. There's only two scenarios, you know? And so those 2 scenarios added up together add up to 100, see? What is this PA and this PA with an asterisk? PA is the probability of A, and PA with an asterisk is like, with apostrophe, sorry, is the probability of not A. Okay, whenever they put like a little symbol thing, it's like not this. See? So the probability of A plus not A has to equal 100% because it is all the scenarios. You either go to them all or you do not go to the mall, and the probability of those added up together is 100% because it's the only scenarios that you have. It's only two options, ¿cierto? Okay, so when they do not use banned substances and they test negative, it's 98%. So that means that when they test positive, it has to be 2%. All right, guys, I know that explanation was a little bit long, but now you are a master at tree diagrams, and that's what really matters. Okay, so that is for part A. Later on, they tell us that we need to determine, and this is now a little bit quicker, but let me just show you the intuition. Yeah, here we have that we need to determine the probability that a randomly selected athlete does not use banned substances and tests negative. All right, guys, there's a lot going on here. See? And I'm sure from class you've seen that sometimes you multiply probabilities and other times you add probabilities. See? And so some of you are probably wondering, when the heck do you use one? When the heck do you use another? You've probably asked your teacher. He's probably giving you some different tips and tricks. The best one that I can give you is that when we multiply probabilities, we need to think of the word and. When we add probabilities, we need to think of the word or. So and is that it happens at the same time, and or is that like it can happen, okay? But it's not necessarily at the same time. Uno o el otro, este es el y. Uno o el otro, y este es el y. All right, whatever. A little bit of Spanish, doesn't matter. um, and so, guys, where's the athlete that does not use banned substances? So that means for this in green, ¿cierto? Does not use banned substances, so we're going this way. And, so we're going to be multiplying, tests negative. So it's 0.94 and 0.98. What almost everyone does is that for part BI, they just write 0.98 because, oh, it's like what they reach, ¿cierto? No. Because there's an and in between, you have to multiply, okay? It's like you enter this world and you end up here. What's the probability of that, okay? That means you gotta do 0.98 times, sorry, 0.94, because of this 4, 0.94 times 0.98, see? Which is this here. Why did that happen? Because whenever you see the word and, you're gonna be multiplying, okay? Cool. So you go ahead and do that. For part BI, the answer is 0.921. So, oops, claro. It would be 0.94 times 0.98. This gives you 0.9212, if I'm not mistaken. If you use three significant figures, it's 0.921 because you count 1, 2, 3. Do you round it up or down? You keep it the same, 0.921. As a percent, it's 92.1%. All right, that is part BI. See, part B double I, okay, part B double I, I'm running out of space, but that's fine. Part B double I is if two athletes are selected at random, calculate the probability that both athletes, okay, so it's two athletes, okay, important, do not use banned substances and both test negative. So it's the same as part BI, like up top, but it happens twice. Ah, okay. So if I were to think about this in words, really think about and or, we have that for part B double I, and this is why it's very important to use the and or words. We have that the first athlete does not use banned substances and test negative, and second athlete does not use banned substances and tests negative. All right, let me put this somewhere where we can see it. Yeah. So as you can see, if you look at my and words that I'm putting in between, we have an and here, we have an and here, we have an and here. And let's also recall that this first part is what we got from part BI. What was the probability? 0.921. 2, ¿cierto? Okay, so that means I'm going to have this 0.912. I'm going to have 0.9212 right here. I have this and, which lets me multiply, and I have another 0.9212. And so 0.9212 times 0.9212 gives me whatever that is. See? So the answer for pair B double I is going to be 0.848609. You can leave it as three significant figures with 0.849 or just, 84.9%. All right, so I know that right now some of you might be a little bit confused, but the biggest idea I have to share is that when you multiply, when you see the word and in the world of probabilities, you multiply. See? And so think about it this way. In order to reach this 98, how do you reach the 98? First you go this way, then you go that way. So first it is a does not use banned substances and tests negative. That is like the biggest idea you can get out of this, okay? Anyways, that is for part B. For part C, we need to calculate the probability that a randomly selected athlete will receive an incorrect test result. Now notice, incorrect is in bold. What are the incorrect test results scenarios? All right, so let's put in red, or actually, let's put in purple the scenarios that are incorrect. An incorrect test result. Not a negative, an incorrect. For example, if someone does not use banned substances but gets a positive test result, then it's fake news. It's literally fake news. They don't use substances, they got tested positive. Here we have something that is incorrect. And so one of the scenarios that I just put in purple is that they do not use and they test positive. Okay, they do not use and they test positive. Okay, so that is the incorrect test result. So that is one scenario. Whoops. So we have that they do not use banned substances. That gives us 0.94. And this is the multiply. They test positive 0.02. Or, kapound, there's a plus sign. Or they use bad substances. Right, uses. But they test negative. And so they didn't get caught, basically. They didn't get caught. So that would be 0.06 and 0 points times, ¿cierto? And 0.29. See? Again, I know this is confusing, so let me go over it just one more time real quick. We have that they do not use, for the first scenario of incorrect, they do not use and test positive. So do not use and test positive, or use and test negative. Okay, that is explanation of each of the numbers, why it's multiply, why it's add. See? So once you have all of that written out, once it makes sense, the adding and multiplying and all that shit, you can put that 0.94 times 0.02 plus 0.06 times 0.29. And see what happens. You get this. This is the answer for part CI. Okay? So that's going to be 0.0362, which is the same as if I tell you 3.62%. Then for part C double I, we have that a random sample of 1,300 athletes at the tournament are selected for testing. Calculate the expected number of athletes in the sample that will receive an incorrect test result. Now, probability is not hard in terms of math, like you're just adding and multiplying shit. but it's very hard to understand why you're doing what you're doing. Okay. And so an expected number, el número esperado de algo, ¿cierto? So the expected number is sort of like, I don't know, I think it's easier to explain with a different example. So let's say that just some random shit, ¿cierto? Let's say that we have a dice, okay? Like a dice, a die, six-sided die, ¿cierto? So you have, I don't know, uh, 1, 2, 3, 4, 5, 6 here. 1, 2, 3, 4, 5. This kind of die. See? Un dado, one. Yeah, it's a dice. See? So this dice has six sides, right? It has a side with a 1, with a 2, with a 3, with a 4, with a 5, with a 6. It's a six-sided die. And what is the probability of rolling a 1, a 2, a 3, a 4, a 5, or a 6? Well, it's six sides, ¿cierto? So for getting a 1, it is 1 out of 6. For getting a 2, it is one of the sides. It is 1 out of 6. So it's 1 over 6 for each number, ¿cierto? If you roll the die, it's 1 out of 6 of getting any of the sides, ¿cierto? Unless it's a loaded die, unless it's like an illegal die, and whatever, ¿sí? So probability is 1 over 6 for each side, ¿sí? Para cada cara. And so let's say, whatever, man. Like, there's 1,000 people. There's 1,000 of us, see? And we all take one die and throw it at the same time. What is the expected number of fours that we're going to have? How many fours do you think we're going to have if 1,000 people throw this dice at the same time? Well, you're going to take that 1,000, multiply it by the probability of getting a 4, which is this 1 over 6, ¿cierto? And that is the expected number of fours we're going to have when 1,000 people roll the dice. How much is this? Around 166. Let's leave it at 167. See? So around 167 people will get a 4 when they roll a dice. Now that is the expected value, okay, the theoretical value. What actually happens, you gotta see it in real life, and let me tell you, it can be very different. See? But what's expected, what's most common, is that we would get 167 people rolling a dice. I mean, rolling a 4. Okay? So again, what's the context? There's 1,000 people. They all roll a dice. What is the what is the expected value of 4s that we're going to get? Well, the probability of rolling a 4 is 1 over 6. So you take that 1,000 and multiply it by 1 over 6. Ah, so you take your amount of people n and multiply it by its probability. Okay. And so in my formula booklet, when you look up expected value, you have this weird thing right here, ¿cierto? Notice how I said it was n times p, so the amount of people times the probability of that thing happening. Well, over here, in a very, very, very fancy way, this right here is p, and this right here, the sum of all your x's is n. Oh, okay, okay. It just makes a lot more sense if I say n times p, right? And if I say the 1,000 people and all that shit. The formula booklet, though, gets way more fancy. And they have to get more fancy. I can't blame them. See, this is like the way you should write it, okay? But whatever, man. We're human beings. We like the intuition, the intuitive version, and so n times p. That's what I'm trying to tell you. For expected number, you're gonna be thinking n times p. What is my n? We have 1,300 athletes. What is the probability that they will receive an incorrect test result? Well, that comes from part CI, so it's gonna be 1,300 times 0.0362, which is the the probability of getting an incorrect test result, and that is going to give me 1,300 times 0.0362 gives me just around 47.06 people. See? 47.06 people, basically. So yeah, if you want to, three significant figures, count 1, 2, 3, this guy, do you round it up or down? You round it up, so it's 47.1. See? That is for part C, part double I. Now, there's something here I can show you that does not have to do with probability, but will help you for whenever you do the test. Notice how this is worth like a million fucking points. It's worth 5 points. See? So what that means, okay, usually when it's worth more than 1 point, usually, okay, definitely when it's worth more than two, is that you have what they call method points, okay? Method points, de metodología, see? So what that means is that you can have the wrong answer, but the right process and get points. Okay, this is just something I want to show you quick, because it's important that you guys know. Over here, as you can see, for question 4, the one we're looking at, you have endpoints here, cierto? Endpoints here. What this means is that you can get method points for, right here, cierto? Right here, they're doing n times p. And basically, you get a method point if your n is correct, because they gave you 1,200, but your p is wrong. If your n is correct, but your p is wrong, you still get one method point, okay? And as you can see, for what's coming, there's a lot of method points all over the fucking place. See, there's method points here, there, etc. What I'm trying to say is, get points where you can. It doesn't matter that it's not 100% correct. You can still get method points. Okay, that's all I'm trying to say, guys. The other thing is that because there's method points, what you needed for part C double I came from part C I. And that's a very common thing that for part C, you need something from part B. Okay, the IB loves to do that. Okay, especially for any section that has part I, part double I, those are definitely connected, dude. So just keep it in mind, you guys. All right, these are test hints, tips and tricks. Everything adds up. Everything helps. Okay. All right, let's move on. Here we have that Team X, that's an interesting name, Team X, are competing in a tournament. There are 20 athletes in this team, and it is known that none of the athletes in Team X use banned substances. And so none of these guys use banned substances. And we need to calculate the probability that none of the athletes in Team X will test positive. All right. This right here is weird. I'm just going to say right away, it's a little bit weird. Okay? What is the main idea? Right now, we're seeing if they test positive or not. Okay? And for testing positive or not, see, we have, give me 1 second. Yeah. For testing positive or not, knowing that none of them, cierto? Notice how here it says none. So none of the athletes in Team X are use banned substances. That means I am in the world that is, let me make a little bit of space because I know I wrote a lot of shit earlier. So if none of them use banned substances, that means I am in the world that is up here. So suddenly, for this part of the exercise, I do not give a fuck about anything down there. This is what I'm working with right now. What's up top? Okay, cool. So we need to calculate the probability that none of the athletes in Team X will test positive. When you work with a binomial distribution, okay, it's when you have only two options, which is what I have right now. I mean, right now, with what they told me, I am in this world here. There is nothing else. This is the only thing in my world. See, they either test positive or negative, period. And so binomial distributions is when you have two scenarios. See, usually it's like, oh, you toss a coin, head or tails. But for these tests of positive or negative, it's either positive or it's negative. And so it's also two scenarios. See? And so one way to do this is that you take the 0.98, multiply it literally like 20 times. ¿Cierto? Um, and that would work. See? That would literally work. You can solve it doing that. So you can do 0.98 to the power of 20. There is your answer. See? Now, there's another way to do this that I would like to show you because it's important to get familiar with the calculator. See? And so when you have your graphing calculator and you identify it's a binomial world because it's only two scenarios and I'm only in this part of my tree diagram, cierto? So it's literally only two scenarios. Um, you can use you can go to the distribution menu, which is pressing second bars, see, to hit that distribution button, and go all the way down to where we have binomial, see? So as you can see, there's a bunch of shit over here. You have binomial, Poisson, geometric. These are different distributions, you guys. Okay, you even have the normal one up here, the most common one, ¿cierto? In this case, you have binomial PDF and CDF, see? Now, they both actually ask for the same shit. So PDF asks for trials, the probability for P, and then an X value, see? Paste is just enter. The binomial CDF, right, asks for the same crap. So what's the difference? Well, I'm immediately going to say, guys, some of your calculators, the CDF is a little different, see? But the classic, the TI-84, we have that the binomial PDF is the probability of um that amount of that exact amount, see? And binomial CDF is the probability of that amount or less. As I was saying, right, we're in the world of either testing positive or testing negative. We have the amount of trials is 20 because there are 20 athletes, and we're looking for the probability that none of them will test positive. And so my X value is 0 because we're talking about none, ¿cierto? Now, what is my probability? Well, I am in the world of testing positive, and so for testing positive, my p-value, my probability for p is going to be 0.02. So this is going to be my p. And so if I go ahead and put into my calculator, normal PDF, because it's going exactly for 0, I have 20 over there. My p is going to be 0.02, and my exact value is going to be 0. See? All right. Go ahead and paste. There it is, which is the same that I got earlier, going like this. See? And so there you have the two ways in order to do it or solve it. See? I urge you to get used to the binomial PDF CDF manner because for some exercises you just have to do it that way. Okay? You can try to do it by hand, but it's fucking annoying. See? Although I think it's kind of cool that you guys maybe know now what your calculator does behind the scenes. Okay? For this next part, the same idea goes down. We need to determine the probability that more than 2 athletes in Team X will test positive. More than 2. See? Now let's remember that I said that binomial CDF gives me that amount or less. And so what I can do actually is that because we're not talking about an exact value anymore, before it was exactly none, ¿cierto? Now it's 2 or more. I can go to my distribution. I can put the amount of trials, which is 20, because I still have 20 athletes, ¿cierto? That hasn't changed. The probability for testing positive, we said, was 0.02. Okay, cool. And it's more than 2, right? So if I put 2 here, what this gives me, actually, because it's the world of CDF, it's the probability of that amount of less. So what I just found is that probability that less than 2 athletes in Team X will test positive is around 0.992931. See? And so right now, what the exercise is asking for is more than, right? And I just found less than because the calculator CDF works in less than. See? That amount or less. I'm going to say right away, some modern calculators, okay? You can like skip the next step I'm going to do because you ask for it to face the other way to look for more than immediately. See? The thing is, in a TI-84, it's always going to give you less than. See? And so right now I just got the less than version, ¿cierto? Now what's the opposite of less than? It's more than. And so guys, this all comes back to the tree diagram, which is the cool part of this exercise, ¿cierto? It's either one thing or another. Your probability has to add up to 1. So it's either more than or less than. You either go to them all or you don't. You either test positive or you don't. And so if less than is 0.992931, then the version of more than is 1 minus 0.992931. And this actually comes from here because from the complementary events world, right? You have that, I don't know, let's say this is my less than version, ¿cierto? less than, and this is more than. See? In order to find more than, you can do the more than is the PA with the apostrophe equals 1 minus P of less than. See what I mean? Which is what I just did here. Ah, okay. So you put that into a calculator, 1 minus this, bada bim bada boom, kapow. You get 0.00706. 0.00706. And so 0.768. So if you go ahead and do three significant figures, you count 1, 2, 3, you do round it up or down, you round it up, so that it gives you 0.00707, which is the same as, well, you can just leave it like that, honestly. The answer key leaves it like that, and that is how you solve it. Okay? So, ladies and gentlemen, number 4 was a hard tree diagram problem, but you also now know pretty much everything you need to know about tree diagrams. So I hope it helped. I'll see you around, and number 5 is coming up.